called Jensen, and I'm here to talk about the Aerospike certification tool, or ACT. My background, briefly, spent most of my career doing system software at a variety of companies. I've been in the engineering organization at Aerospike since 2019. And technology-wise, focus on data center technology and performance. Today's talk is roughly divided into two parts. The first part is going to be describing what ACT is and how to use it. The second part is going to be how to derive useful metrics from it. So ACT is a performance tool that simulates I/O patterns that would be performed by a cluster node. This is kind of the key difference between ACT and a more conventional benchmark program. It is, as we'll see, it's really modeling what an Aerospike cluster node would do in terms of I/O. It is a GitHub community project in the Aerospike ACT repository, so it is open source with a permissive license. The bundle has 4 key executables. ACT prep is a utility to prepare the SSD for the tests. There are 2 programs, ACT storage and index, that actually are generating the I/O transactions. ACT storage is the one that's going to be talked about today. It models Aerospike's hybrid memory architecture, which maintains the index in DRAM and the data in SSD. ACT latency is run to analyze the results of either ACT storage or index. When they're run, they produce output, which ACT latency can extract histogram information from. And that is one of the key goals of ACT is not really to look for pure performance, but performance while simulating a realistic workload and in sort of a real world scenario. One other thing about ACT is the current version is 6.2. And because it is emulating algorithms in the server, it is compatible with Aerospike database 4.7 or greater. You want to use the previous version if for some reason your sizing exercises are on something before Aerospike 4.7. ACT X notation, I want to talk about this up front. This is commonly how throughput results are quoted. You'll hear of a device being 90x or 122x. It is based on an ACT run that's configured in a very specific way to allow different devices to be compared. The key thing is the read-write ratio, which is specified by 2 configuration parameters are in a 2-to-1 ratio, and you take the default values for all the other configuration parameters, things like record size, and then you have to run 24 hours, and that run must complete. ACT will abort if it falls behind, and when you run ACT latency, 95% of the transactions should complete within a millisecond. That's kind of the key. If you do that, then to convert your results into an X rating, you just add the read and write requests per second, divide by 3,000. And as you can see on the slide, you can go in the other way as well. ACT prep only needs to be run once, and it is invoked very simply with the block IO device that you want to prepare for testing. It puts it into a known state. It will destroy all the data. And operationally, it is pretty simple. It fills, it makes two passes. The first pass, it fills all the blocks with zeros, and then it fills them with random data. Some operational pragma to use ACT prep. First, you want to format the device, create any partitions you're planning. It only needs to run once before you start your testing, and does not need to be run for subsequent runs. It is fine to run it in parallel on multiple devices. Depending on your system, it's likely to be faster than doing them serially. One caveat is if you're partitioning, you be careful not to accidentally specify the raw device /dev/SDA, because that'll wipe out the partition table and you'll have to start over. Okay, I've got ACT storage and ACT index here. They're very similar. ACT index does additional IO because in that configuration, the indexes and the data are both on SSDs. But the focus of this talk is ACT storage, which simulates the hybrid memory configuration. These programs take one command line argument, which is the configuration file. We're going to go through those configuration parameters shortly. As it runs, it is producing voluminous output, and you want to redirect that to a file so you can run ACT latency later on. I'm going to run through some of the key configuration parameters to give you a flavor of what you're setting up. The first one is a list of the devices. Next is read requests and write requests per second. And important thing to understand is, unlike a lot of benchmark programs where you launch and they run as fast as they can, with ACT, you give a target and it will generate requests at the rate you specify. ACT is more interested in latency, so it will, if it runs the completion, then you have some results you can look at. But if the drives fall too far behind, they will, the program will abort. So the methodology that we'll see is you make multiple ACT runs, tweaking the configuration until you have reached a local maxima on the throughput with acceptable latency. These next couple of parameters this gets to the fact that this is not just a simple load generator. You actually specify the load in concepts that would be known to the Aerospike cluster, such as the size of the write block. That large block is used when you're writing records, for example. They're aggregated. The replication factor is directly analogous to the Aerospike cluster replication factor, and ACT also simulates the defragmentation process So you can specify the threshold where you want blocks to be defragmented. There are some time-related parameters. The test duration seconds is the key one. The other ones you're not likely to change very often. The report interval is how often the histograms are output to your log file, and that is 1 second by default. There's usually not a good reason to change that. Likewise, the histograms that are all expressed in milliseconds, but with some low latency SSDs, that's too coarse. You can override that with the millisecond histograms parameter. Max lag seconds is significant. We'll talk about it later on, but it controls how far behind in seconds the drive can fall, and that is measured based by since you're giving it fixed read and write rates, it essentially can it knows when a request should have completed, and if it takes longer, if it completes at a later time than it should have, that's recorded as lag. It defaults to 10 seconds. So if your drives fall further than that behind, the test will abort. And finally, if you are actually sizing for a deployment rather than trying to do a standard X rating, you can control the record bytes, essentially control the record size or size range, and you're updating, how updates versus replacements. And you would base those on whatever application you were planning to deploy. There's a couple of uncommon configuration parameters I just want to mention briefly, mainly because they can send you off to do a lot of Googling. The compressed percentage, normally records are just filled with random data, but you can also specify that they're filled with a mixture of random data followed by a big block of zeros. And if you're testing a drive that does onboard compression, which some high-end SSDs do, and you know the characteristics of your deployment, then this can be used to assess the capabilities of those drives. If you're doing host-based compression, you don't want to change this. The scheduler mode, the short answer is it's no longer relevant. It made sense for rotational media when you had host drivers doing seek reordering. Defaults to no op, and with SSDs, you don't need to change it. Commit to device, I'm mentioning only because it changes, has a pretty drastic effect on performance. Normally, Aerospike records will be read individually, but on the write, they are aggregated into large blocks. If you enable commit to device, it will write each record. It won't aggregate it. It'll write it immediately, and it does it synchronously, so it waits for it to complete. That will have a huge impact on performance. So unless you're using a server feature like durable deletes where this is relevant, you want to stay away from it. This is actually what the ACT storage looks like under the hood. There is a main thread that parses the configuration file and then launches up to 4 groups of threads that are actually performing I/O on the SSDs, seen off on the left, and is outputting intermediate histograms to a log file as shown on the right. And just looking at these briefly, the default for the large block read and writes is there are 128K blocks. There is one thread created for each device. So these activities are parallel across devices. And then we'll see what they are used for. The service threads are used for when you're reading a record, individual record, and you can specify how many service threads are. And that's an important part of the assessment. I'm going to skip Tomb Raider, talking about that. It is included here for completeness. And real briefly, the large block reads, they're actually simulating multiple server activities that use large blocks. And the big one is the defragmentation. The large block writes are also used for defragmentation, and as I mentioned, normal record writes are aggregated. Service threads default to 5 times the number of active cores in the system you're running the test on, and as I said, those simulate the client reads. That 5x is something you want to experiment with. The default is not necessarily going to give you the best performance. So these threads are, to give an example, which is shown here, the large block reads it essentially just generates using random number generators and computation, generates transactions at whatever rate you've specified. And I wanted to show you how complex, though, these rates are driven, because again, large block reads are used by multiple components of the server. This diagram is showing that actual calculation, and the blue boxes are actually ACT configuration parameters. So those are sort of the inputs, and you can see there is a variety of multiplies and divides. Essentially what this is telling you, though, is that your large block read rate, it depends on multiple config parameters. Some of them it's directly proportional. Some of them it's inversely proportional. Talking now about the output format, which is what's processed by ACT latency. There are when you look at this file, it's documented in the code. There's really not a formal documentation, but it's a very simple format. There's a header that echoes back your input configuration parameters and some derived parameters. And then every report interval, which is by default 1 second, it will write intermediate histograms showing cumulative IO operations. Some of these, they are both per device and per category. And as I said, you capture them and then you can run ACT latency on them, which is the next subject we're going to discuss. This is a Python script. You can control the formatting a little bit with some command line parameters. The main one you're likely to look at controls the level of aggregation or intermediate slices. We'll see an example on the next slide. The key thing is that it summarizes and output the histogram statistics, And the slices sort of show you what's going on during the run. It also prints at the end globally the average and maximum latency. So a couple of things to observe with the latencies is those intermediate slices can show you trends. They can show rough patches where the drives are having trouble keeping up, or and recovering, hopefully. And the max latency at the bottom is used to determine whether the run passed or failed. This is particularly important if you're calculating a X rating. The latencies essentially point you in one of two directions. If they're really low, that means your targets weren't aggressive enough. If they're right on the edge, or if you actually fail, then you went the other direction, and you need to dial one of the configuration parameters back. Here is a short example showing a 12-hour run, and it's being run with the default slice interval of 1 hour. You can see it echoes back the configuration parameters that were used to generate this. And this run is interesting because you can see that it did pass. But you can see during hour 6 is when it encountered some difficulties. If you were running this in the cloud, that could indicate network throttling or a noisy neighbor, or it could indicate something the firmware is doing, particularly something called garbage collection, which we'll talk about near the end of this talk. We've now arrived at the second part of the talk, which is the certification methodology. So this is really a guide to how to use the ACT tools to find the sustained maximum IOPS over a 24-hour baseline. And that baseline really is important because sometimes drives, sometimes even 24 hours you might want to go further. You can see drives that sometimes will get up to the 16th or 17th hour and then fail. So the first step is to define your traffic profile, which is, these are things like your record sizes. And again, note, these are not raw benchmark parameters. These are expressed in Aerospike server terminology. Your read-write ratio, update rate, how aggressive you are with defragmentation. You want to get those set. If you're just calculating an X rating, then you take the defaults on these, and you wouldn't change any of them. The hard part is that what you're really doing is iterating through a search space that's pretty large, because there are at least 4 things that are going to influence the outcome: the read-write requests per second, the number of devices, the number of partitions, and the number of service threads. So this part is really telling you how to minimize the convergence time. What you're actually doing is that this is a well-known computer science paradigm. It's you can think of this as a form of gradient descent, or there's also some similarity to linear programming problems. So the first, as I've said, it's an iterative process. The most important thing is to pick a good starting point. And the definition of a good starting point is you want to be close but under. And the reason for that is going over can provoke garbage collection, which can cause you to spend some additional iterations. One tip for doing that is take a look at the drive you're using, see if it's already in the Aerospike certification page for the X rating. That can give you a very good starting point. Or if it's not there, you can look for something that is a close match on the X rating, and then compare data sheets, which will tell you, most of the data sheets will tell you basic sequential and random read-write IOPS. And then as you're iterating, you don't want to run the full 24-hour runs until you get near the end, because it chews up a lot of time. So 1 to 4 hour runs, better idea, especially if you're just trying to collect enough data to to examine latencies at high granularity. You do want to pay particular attention to runs that are on the edge of passing or failing. And one of the best ways to do that is when you generate the report, instead of having the slices be hourly, make them at 10-second intervals. You will get a lot more slices, but you can look at things that would be averaged out. And in particular, one of the things you want to count is the number of times it's going over 5% of the samples needing to take longer than a millisecond. This indicates the stress the drive is under. If that is very frequent with the slices, then you are too aggressive. If that was like a 4-hour run, you probably wouldn't want to try a 24-hour run without changing something. And this, again, clearly, if you fail, your throughput targets were too high. And if you have a passing run, however, then you combine with the short runs that sort of show you performance in the adjacent search space, then you've got pretty good confidence. You have enough data points to say this looks like a local maxima, which is what you're looking for. I want to talk a little bit now about configuring service threads. This is one of the, this is probably, I would say, a good place to start, because on a number of systems, quite often 5 times is too high. And the thing with service threads is if there's too many, they're not really, you're inducing a lot of overhead, because essentially you have too many threads, but you still have to schedule them. That's going to reduce performance. Good rule of thumb would be to reduce that to 3x the number of cores, or even start there. A lot of systems, the best performance is closer to 3x. But don't just arbitrarily go low as well, because if you go in the other direction, then you're leaving parallelism that you could be exploiting on the table. And you can spot that by looking for a lot of idle CPU and short IO queues. Another thing to do sooner, in other words, before you start cranking the actual read-write rates, is settling on the number of partitions. They can afford a lot of additional parallelism. It really depends how much you can get. It depends a lot on the internal structure of the drive, how the flash chips are laid out, what controllers used, what algorithms were executed by the firmware, and that latter is this is all secret sauce for the SSD vendors. So any insights into behavior have to be determined empirically. but it does make a difference. We have seen cases where you can have as many as 12 partitions and even 16, I think, and improve performance. One caveat is this is fine if you're in a lab setting and you're controlling the physical hardware. If you're in the cloud or a hyperconverged architecture platform, the devices presented to you might already be partitioned. They are probably abstracted away. If so, I'd just take a look, especially in the cloud, at the drive capacities. If you're being offered drives that are less than 500 gigabytes, partitioning is not likely to buy you much, if anything. Rough strategy for doing that is pick a starting point. I would say if it's especially with a larger drive, you might want to start with something like 4 partitions or more, and make a short run to assess the latencies, and then by essentially iterate by looking at what happens with each run, which way your performance goes, and this is essentially a binary search paradigm. And at some point you'll see diminishing returns, and at that point you can stop. A couple of additional tips. One is overriding the max lag seconds. Again, this by default 10 seconds. It is how far your IO requests are allowed to fall behind what the drives should be dispatching. If you increase it, you are you're letting the system tolerate more lag, and that's going to hurt your histograms. By the way, though, that's likely to push your histograms in a bad direction. If you decrease it, you're putting the run on a shorter leash, so you have less room to fall behind before you'll get aborted. The extent to which they're out of balance is actually a good heuristic for assessing the stress on the drive. So this can give you, especially in the early stages where you haven't really converged, if you are you just want to see if they're in balance. If they're in balance, and that along with the latencies is kind of a good sign. You can completely disable the lag mechanism by setting it to 0, but this usually isn't very useful. The drive will complete, but you won't have a good idea of what the actual maximum lag was. Some things to avoid that I haven't explicitly mentioned. Big one is you for the most part you want as homogeneous a configuration as possible. You don't want to mix SSDs. You don't want to mix partition sizes. In most cases, we've already talked about service threads. One last caveat is if you overshoot your throughput target, in other words, your read and write rates were too aggressive, the run will fail. It'll abort because the lag was too high. You don't want to immediately start another run. And the reason is if you're pushing the drive hard, you may well have triggered garbage collection. And the thing about garbage collection is it's a background process, but it can also be going on even if you're not putting any load on the drive at all, because if you drove it really hard, it could be trying to catch up. So if you started on another run immediately, that's going to hurt your performance. This is an example of write amplification. And so the best advice is let it rest an hour or two before starting another run. I'm going to talk very briefly about garbage collection. The key thing to understand is there's a hierarchy on NAND flash drives. There's the pages, which are they're typically 4K bytes. These are this is the smallest unit for reads and writes. This is what you're used to. You can read any block, any page. You can, but you can only write one if it's been erased. And the problem with erasing is you can't erase a single page. You can only erase at the block level. And a block typically has hundreds of pages, and it also takes a while to do that erase. So the firmware has to, garbage collection is essentially trying to relocate pages that have been written but aren't currently being used by the host, and collecting them all so that you can do a block free, and then those pages are available for allocation. The main thing to remember here is if you update a page, what you actually have to do is allocate a new page and do the write there, and then mark the old one as available for freeing. And that shuffling can chew up a lot of bandwidth. Last topic. This is an example of there's nothing to stop you from writing your own analysis tools on the output from ACT storage. A simple way to do that is this shows a Perl script that just transforms the ACT log into raw IO histogram counts and comma separated values. You can open that directly in Excel, and you can then graph. You can do whatever analysis you want. This graph on the right is just showing IO rates per second, and so you can actually those regular spikes. That's an indication probably of garbage collection. When the reads go up, that probably means garbage collection is completed and you have a lot of free pages. So getting a new page for a write is very fast. You don't have to stop and find one. Likewise, if garbage collection is in process, or you don't have a lot of free pages, you can go the other direction. This is the end of the talk.